In the last video clip, we looked at molecular compounds. For this clip, we change our focus to ionic compounds. Now, you're already working to memorize the different ions, their names, and their formulas. So let's look at a review of where these names come from. Remember, monatomic ions are ions that are made up of a single atom that gains or loses electrons. In general, metals will always lose electrons to become cations, and most nonmetals will gain electrons to become anions, or negative ions. We also have a sheet of polyatomic ions that you're working on. The polyatomic ions form when you have a group of atoms that are covalently bonded, and collectively the entire group gains or loses electrons. The most common type of polyatomic ions are called oxyanions. Oxy because they contain oxygen, anions because they are negative ions. Now, going back to the monatomic ions for a second, the monatomic cations are the positive ions. These are the ones that are based on metals. The name of the ion is exactly the same as the name of the element. So if a lithium atom loses an electron, it becomes the lithium ion. A magnesium atom that loses 2 electrons becomes the magnesium ion. The name itself stays the same. The monatomic anions are a little bit different. If they gain electrons to become a negative ion, we change the ending of the name of the element to "ide." For example, when oxygen gains 2 electrons, it becomes oxide. When nitrogen gains 3 electrons, it becomes nitride. Or fluorine gains an electron, it becomes fluoride. Now, for our monatomic cations, yes, the names of the elements stay the same, but often there's more than one form of ion, in which case we use Roman numerals. Now, looking at the periodic table, some of the elements we can figure out their charges pretty easily. For example, in the S block, which is this column, and helium. In the S block, when they become ions, they lose 1 electron, so they always become 1+. In the second column, they lose 2 electrons to become 2+. For these 2 columns, we do not need Roman numerals. Moving on to the D block, though, the D block almost always have more than 1 possible charge, so we need Roman numerals for most of them. Although this is by no means a complete list, there are a couple ions that can only take 1 form that are here in the D block, and even the P block metals. Those won't need Roman numeral. If you remember these 3, aluminum, zinc, and silver, you should be okay. So no Roman numerals on group 1 or group 2, because group 1 is 1+, group 2 is 2+. We do need Roman numerals for all of these metals, except aluminum, zinc, and silver. And the charges of aluminum, zinc, and silver are 3, 2, 1, respectively. No Roman numeral needed. Now, the P block metals, and there aren't a lot of them, we mainly focus on lead and tin. We do need Roman numerals for those, and lead and tin could either be a 2+ or a 4+. For the polyatomic ions, it gets a little bit more complicated. Let's look just at the oxyanions, which are the negative ions with oxygen. They're named based on how much oxygen they have. For the most part, they're all named on whatever the first element is, and the ending reflects how many oxygens. If you see "ite," that means less oxygen, and when you see "ate," that means more oxygen is involved. If there's more than 2 forms, for example, there are some that can form 4 different ions. The 2 of them that have the less oxygen end in "ite," the 2 with the more oxygen end in "ate," and we use prefixes. The less of the less is hypo, and the most of the most is per. For example, looking at chloride, Cl is 1-. When it joins oxygen, it can become ClO, ClO2, ClO3, or ClO4, all of which have a -1 charge. Now we split them. These 2 with the less oxygen become chlorides. These 2 with the more oxygen become chlorates. The least of the least is hypochlorite. The most of the most is perchlorate. Now, when naming a compound, all we need to know are the names of the 2 ions involved. We just put together the names of the 2 ions, and that gives us the name of the compound. Note There are no prefixes. There's nothing to tell us how many of each element there is. And the reason why is because these are ions. They all have charges. We've learned before that ionic compounds are always neutral. So however many positive charges we have, you have to have the same number of negative charges to balance them out. So for example, in this compound, I have 2 aluminums and 3 oxygens. But I know that aluminum always has a 3 plus charge and oxygen always has a 2 minus charge. So I can figure out how many of each it would take to create a neutral compound. So I'm looking only at the names of the 2 ions. The first one is aluminum. The second one is oxide. And when we put them together, we get aluminum oxide. Now the charges do balance out, because if I have 2 of this and each one is 3 plus, this side of the compound would be 6 plus. I have 3 of these and each are 2 minus, so this side would be 6 minus. A 6 plus and a 6 minus balance out, giving us a neutral compound. In this example, we have an ion of copper and an ion of chlorine, so it becomes copper chloride. The only problem is chlorine is not on that short list of elements. It does need a Roman numeral. So the Roman numeral tells us which version of copper it is. There's 2 types of copper, copper 1 plus or copper 2 plus. The reason why we know this is copper 1 is we use the second element to figure out the charge of the first. The chart of ions tells us that chlorine always has a -1 charge. Now you only have one of each of these elements, so if chlorine has a -1 charge, then the copper must have a +1 charge to balance it out. So that gives us copper 1 chloride for the name. It's not always going to be copper 1. In this example, we have CuCl2. Again, we have a copper ion and a chloride ion, but it's no longer copper 1. We could use the second ion to figure out the charge of the first. Chlorine has a -1 charge, but there's 2 chlorines. So the chlorine side of the compound is 2 negative. That means the copper side must be 2 positive. You only have 1 copper. That copper has to have a charge of 2 plus to balance out the chlorine. So in this case, my compound is copper 2 chloride. Few examples. The first example is zinc and chloride. Zinc is on that short list of elements that don't need a Roman numeral. Group 1, Group 2, aluminum, zinc, silver. So, no Roman numeral, and it's just zinc chloride. My second example, I have potassium and iodine. Potassium is in the first group, so it doesn't need a Roman numeral. So when we put it all together, it's just potassium iodine. The next one, we finally need a Roman numeral. This is iron, this is oxide. Oxide has a charge of 2 minus. So the only way this compound is neutral is if the iron is 2 positive to balance that out. This is iron 2 oxide. In the next example, I still have iron, I still have oxygen, but the charges are different. Oxygen still has a charge of 2 minus. That's always the charge of oxygen. But this time we have 3 of it. So what is the charge of all of the oxygens combined if each of the 3 is -2? Answer is it gives us -6. If that side's -6, that side must be +6 to balance it out. But I have 2 irons. My 2 irons means each one has to be 3 plus. Now a little shortcut to figure out the charges too. When you put the charge here of oxygen, you see this 2 here and this 2 on iron. If these 2 numbers match, then these 2 numbers will also match. So if those match, then there has to be a 3 plus up here opposite the 3. So the name of this compound, iron 3 oxide. Okay, here we have copper and we have sulfur. The charge of sulfur is 2 minus. There's only 1 sulfur. We again notice that these numbers match up, so that actually means these will match up. There's a 1 understood to be here, so the copper will be 1 plus. Now why does this work? Well, you have sulfur -2, and there's only one of it, so that whole side is -2. That means this whole side has to be +2. If the coppers will total +2, but there's two of them, divide that +2 by 2, and each one has a charge of 1 plus. So it becomes copper 1 sulfide. Now I'd like to rehash that for 1 second, just so that we keep it clear in our mind. When we're looking for the charge of the first element, you have to use the charge of the second element to get the first element. And as long as the charge of the second element matches the subscript on the first element, in other words, these two numbers match, these two will also match. And that makes it a little bit easier to figure out. So here, those two match, so these two match. Now, in my last example, I have magnesium, group 2, does not need a Roman numeral, so it's just magnesium. And the second element is bromine, with the ending changed, becomes bromide. Now, all of these examples are ionic compounds, but they're also made up of monatomic ions only. When we add in the polyatomic ions, it looks more complicated, but it still works the same way. For example, NaNO3, we have to find the polyatomic ion. I find it helps to put in parentheses once you find it, but since most of them start with oxygen, or rather have oxygen in them, start on the oxygen and work backwards. So look for an ion that has 3 oxygen, but has a nitrogen with it. And when you look at the chart, you will find that. Now if we keep going backwards and add Na, there is no ion that has all of this. So my ion is NO3. That means that I have sodium, which is in group 1, so it doesn't need a Roman numeral, it's just sodium. And NO3 is called nitrate. So when we put it together, we get sodium nitrate. In this example, our polyatomic ion already has parentheses around it, and our polyatomic ion is SO4. So that is known as sulfate. It's paired up with aluminum. Aluminum does not need a Roman numeral, so we put the two parts together and we get the name aluminum sulfate. Next example, the Roman numerals finally creep in there. We have NO3, which is nitrate, and we have copper. We need to figure out what form of copper it is, so we look up nitrate on the polyatomic ion sheet, and it has a charge of -1. Again, this charge matches this subscript, so I know that this is going to match the charge of copper, making this copper 2 nitrate. One more time. If nitrate's -1 and you have 2 of it, that means the nitrates are -2. The coppers have to be +2. Again, copper 2 nitrate. Okay, some examples on the next slide. We have here SO3, start with oxygen, work backwards. That's your polyatomic ion. And the first element is iron. Iron has to have a Roman numeral, so I look up the charge of SO3, and it's 2-. You have one of each of these, so if the sulfate is 2-, then the iron must be 2+ to balance it out, and I get iron 2 sulfite. Next example, starting with oxygen and working backwards. There is an ion that's NO3. If I try to add an H4 to it, I won't find it. So I look up NO3 and I find that's nitrate. I then tackle this part of it. Luckily, there is an ion that has that whole formula, NH4, NO3. NH4 is ammonium, NO3 is nitrate, and we put it together. Next example, again, start with oxygen and work backwards, add the chlorine to it. First element is potassium, group 1, no Roman numeral needed. Second part of this is chlorite. So put it together and get potassium chloride. Next example, I have magnesium, group 2, no Roman numeral, and PO4 is phosphate. Get magnesium phosphate. For this one, OH, hydroxide, NH4 we already saw that was ammonium. I put it together, I get ammonium hydroxide. And in this one, magnesium, no Roman numeral needed because it's in group 2. And CH3COO is acetate. Okay, so in this video we focused on writing names of ionic compounds. In the next segment, we'll look at how to write the formulas if you're given the name.